Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at graph algorithms. We will be looking at definition of graphs, and we will be looking at how graphs as combinatorial objects can be applied in our field. Now, what is a graph? Many of us think of graphs as a plotting of some line on an xy plane. This is a class of object where we have some set of elements or vertices, say v 1 to v n, and we will usually represent it as an element of some set, and there are edges. Now, edges are pairs of vertices. So, it is like we say that a vertex I and vertex j is related to each other if there exists an edge between them, or in other words, if v I v j is an edge in this set. So, usually we denote as edges as some set of pairs. Now, when we talk about graphs, usually we say that G is a graph. G is a standard notation for graphs, and it is specified by giving these two sets V and E. V standing for the set of vertices and E standing for the set of edges. Now, if I say that U V is a element in this edge set, it means that there exists a relationship between U and V. Now, when we are defining edges in general, we do not require that if U V is there in this set, then V U is also there in this set, or in other words, I can talk about various kind of relationships. For example, say parents child relationship. So, we will draw an edge between A and B if A is a parent of B, or in other words, in that sense say that A comma B is in the edge. But if A is a parent of B, that does not mean that B is a parent of A. So, in that respect we will not draw an edge. So, it is not necessary that if U V is in this set edge, then V U is also in this set edge. But if it does happen that if U V is in this set edge, then it implies that V U is in this set edge, then we call that an undirected graph. A graph, as I told earlier, is a way of expressing some relationship. So, it depends upon what kind of relationships we are talking about. We will see many examples of how things can be worked out. Also, an edge can be assigned an weight. For example, say we say that between point A and point B there exists an edge if there exists a road from A to B. Now, we might also want to specify the length of the road, and that we can add as a weight of that edge from A to B. So, if a graph is given to us with weights on the edges, then we called it a weighted graph. There are some other basic definitions of graphs that maybe many of you have seen. For example, if there is an edge from U to V, then we say that V is a neighbor of U, and the set of all neighbors of a particular vertex U is called the neighborhood of the set U, and the size of the neighborhood of a set of a vertex U is called the degree of U, or in other words, degree of U is the number of vertices which are related to u, or for which there is an edge from u to that element. Let us consider some example. Say for example, here are some set of vertices. Now, these vertices, as we have told, is just a set of elements in a set, but when we want to describe it, or for our own better understanding, we usually represent these elements or vertices as these circles, and we name each circle depending on some condition. Here we have just randomly named some set of vertices. So, we have 7 vertices here which we have named A, B, C, D, E, F, G. They have been just drawn on this plane. Now, what are the edges? Edges are relationship between these vertices. So, for example, if somebody says that there is an edge from A to B, or rather if A comma B is a element in this set edge, then we will draw a line between A and B. Similarly, if A and D is a element in the set edge, then we will draw a line between A and D, and so on. So, we can have something like this. We have, say, here AB is an edge, AD is an edge, BD is an edge, but BF is not an edge, or similarly say AE is not an edge. So, this is a very nice and concise way of representing relationships. Here one thing to note is that when I say edge, I mean that if AB is an edge, then BA is also an edge. So, there is no ordering about which one comes first in an edge, and since there is no ordering, this is known as the undirected graph. In an undirected graph, if AB is an edge, then BA is also an edge, and we represent it with just a single straight line without any other condition. So, this just says that AB is an edge. But if for example, that was not the case, say if BA is an edge, but AB is not an edge, or in other words, in the relationship between objects, BA is a relationship and AB is not a relationship, in that case we would have to indicate it somehow in this pictorial manner, and usually we do it by putting an arrow on that edge. The arrow designates which one is related to which. Here is an example of a weighted graph where we have put weights on these edges, and here is an example of weighted directed graph. Now, here say for example, DA is an edge, but AD is not an edge. So, how do we represent it? We represent it by making this edge look like an arrow. The arrow points that AD is an edge and DA is not an edge, and there might be edges like this, like AB, where A is pointing to B and B is also pointing to A. That means AB is an edge and BA is an edge. So, this also is a very concise and beautiful pictorial description of a graph. Always remember that the graphs will be given as sets. So, as an input it will not be given in this pictorial manner. The edge weights, as I told, can denote various things, and we will see it today and in some future lectures about how those edge weights can be very useful. So, what is the advantage of this graph? It is a mathematical way of expressing relationships among objects. Secondly, it is very simple, and thirdly, it is very general. We will see in the rest of the lecture today that there are many problems in real life that can be represented as graphs. Now, once we have represented something as a graph, so many of our real life problems can be formulated as a graph problem. So, instead of solving the main real life problem, it is same as solving the graph problem. Okay, of course, that does not make our life simple. There is a real life problem and we have the graph problem, but the fact is that the graphs are such a general class of objects that we can study them without even worrying about the real life problem, and as and when required we will use the graphs to solve our real life problem. So, in some sense graphs are an abstraction of all the or many problems that we get in our real life, and So, solving or understanding graphs is a very useful thing, and that is why we will be spending quite a few amount of lectures on understanding graphs and graph algorithms. Now, let us look at one example. So, this is known as the friendship graph. So, each person is a vertex. So, I represent each of the human beings on the earth in a vertex. Now, we say that any two persons, if they are friends, then I draw an edge between them. This is a description. Of course, it is a different thing how do we get such description or how do we understand who is a friend of whom and so on. But this kind of concepts have been used a lot in understanding social networks like Facebook. For example, in the people who are familiar with this kind of sites like Facebook and Twitter and so on, one can represent each of the individual or each of the individual profiles as a vertex. And now, if two vertices or two profiles are friends with each other, then we will draw an edge between them, and thus we will have a very nice description about how the whole Facebook looks like. And once we have that, we might want to use that understanding, or we have to use our understanding of graph to understand how is Facebook behaving. So, here is an example of a friendship graph. It is a real example of friendship graph. Now, as it turns out that there are clusters here. So, it is not hard to imagine clusters can be something like friends in a particular college, they are all friends with each other, and these clusters can be various colleges. So, Facebook seems to be becoming more friends among people who are in the same college seems to be becoming more friends with each other, but across colleges people are not becoming friends. This graph can also represent things like Facebook is very popular in a particular country and not particular popular in another country. So, how can Facebook use it for its own advantage to where to expand and where not to expand? The another thing to understand is that, say for example, I am here and you are there. Now, I have some Facebook friends, they have some Facebook friends, and similar, and you go on like that until a point will come when you will come in this chain. So, question is that it is interesting to know how much distance is there between you and me. In other words, I know a person, that person knows somebody, that person knows somebody, maybe that person knows you. If that chain, if it is it very long, or is it like just a 4 persons in the whole chain? So, basically we can reach each other just by a chain of 4 person. This indicates the distance between elements in a graph, and to understand the distance between elements, we have to again go back to this graph and understand how connected is a society. So, this is one example where graphs are used. Let us take a small break now. After we come back, we will look at much more interesting examples. Welcome back after the break. So, before the break we looked at the friendship graph. There is another such graph which is known as the internet graph, sometimes also known as the web graph. So, here basically each website is a vertex and we draw an edge between them if one website has a link to the another website. So, this is used by Google a lot, and this is called as the web crawl. This is how Google works. For example, here is a real life example of how the websites in general look like, and you can see by looking at it vaguely already that there are particular nodes, like as it is shown in this small picture here, that which are like the central nodes from which all of them are connected. So, there are some websites which links all of them, some maybe the news channel websites or something like that, and the rest of them are just individual websites which do not exactly connect that much with each other. So, again this is an example where representing our problem in a graph form is helpful to understand our society. There is another more day to day life application is the road network, where we have vertices and we have cities and the edges are the roads, and we also put weights on the edges depending on the distance. For example, say here is a map of Europe, and here it says that from Amsterdam to Berlin it is, we have an edge because there is a road between that, and the distance between Amsterdam and Berlin is 690 miles. Similarly, from Berlin to Prague is 380 miles, and so on. Now, say if you want to go from say Florence to Amsterdam, how do we go? Of course, one can go through Brussels, Paris, Geneva, Milan and then Florence, or one can go through Berlin, Prague, Munich and Florence and so on. So, there are multiple paths or roads that one can take. Now, which one is the smallest one? This is the typical question we ask all the time in our life, correct? We have to go from one place to the another. What is the shortest distance that we need to go, or what is the shortest path to take? Of course, we need to solve it, and when it comes down to lots and lots of vertices and lots of points, it is very hard to compute which route is the shortest route. But once we have represented in terms of a graph, then we can solve a graph theory problem and hence get something out of it. Another example is the air or rail connectivity, where say all the vertices are airports and we denote by an edge if there is a flight between two airports, and say here is a rail or air connectivity of India, and basically we can see that there are various edges which say that from Kolkata there is a flight to Bombay, from Chennai there is a flight to Bombay, from Chennai there is a flight to Bangalore and so on. But now, if one wants to go from Leh to Cochin, what is the least number of hops one would make? And that is the question that we need to ask, mainly when you are going via say train or plane or any such thing. What is the least number of changes I need to make? The idea is just to sit down in a plane or train and just go, and the less the changes we have to make, better it is. And how do we solve it? The solving is of course via the same technique, where we represent it in a graph and try to solve it accordingly. Now, here is another example, but there are many examples in real life which can be designed as a graph problem. So, in general, studying the structure of graphs is a very important field. It is like a proxy to solving all the other real life problems. So, if I know how to solve various graph theory problems, then various real life problems can be modeled in graph theory, and we can use our known algorithms to get our answers. And that is why graph theory is such an important subject in the field of algorithms. Now, let us look at one concept of graphs. It is known as the vertex coloring. So, we have a graph G which have a vertex set V and an edge set E, and we want to color these vertices with k colors. In other words, we have colors, we will just assign each vertex with a number 1 to k. 1 to k are just numbers, say, but under the condition that if there is an edge between V I and V j, then I cannot color both of them the same color. So, any two neighboring vertices must have different colors. It is a simple question that given a graph, how many colors do I need to color the graph? You might be thinking that this question is something very artificial, and why would one even want to care about it? So, for example, here is an example of a vertex coloring, where we have a graph G and we want to color it using colors. So, we color A with green with red, then we can color B with blue, C again we can color with red, and D we cannot color with red or blue because it is a neighbor of A and B. So, we color D with some new color which we call green, and similarly E we cannot color with either red, blue and green, and we color it with white color, and similarly F and G. Now, this is the coloring of this graph. Now, how many colors have we used? We have used only 4 colors. red, blue, green and white. Note that I leave it as an exercise to check that this particular graph can be colored with just 3 colors. So, it is not obvious that this graph can be colored with 3 colors. So, in other words, if I just give you a graph and ask you how many colors is required to color it, it is not an easy answer. But this problem is something very important or useful for various interesting fields. For example, here is a map of India and we want to say color each of the states with a different color, such that no two neighboring states are colored same. For example, if Maharashtra is colored green and Andhra is also colored green, then we will not understand the boundary between Andhra and Maharashtra. So, we want to color Andhra and Maharashtra as different colors. So, similarly is Tamil Nadu and Kerala and so on. So, how do we solve it? Here is the graph theory problem of it. For each state, we draw a vertex, we put a vertex there for say Tamil Nadu, Kerala, Andhra Pradesh, Maharashtra, Madhya Pradesh, Orissa, Chhattisgarh, and we keep on doing, put an edge for each of these states. Now, what do we do? If two states have a common boundary, for example, say Karnataka and Andhra Pradesh have a common boundary, we draw an edge. It basically saying that, see, here is an edge, so you cannot violate this edge. If Karnataka is colored something, Andhra Pradesh cannot be colored something same. Similarly, we draw this edge between Andhra Pradesh and Tamil Nadu, Tamil Nadu and Kerala, Kerala and Andhra Pradesh, and we keep on drawing edges depending on various whether they share a common edge or share a common boundary or not, and we keep on doing it. Now, once we have done with this, so we have a graph or something and we can throw away the map, and let us see what happens if we throw away the map. Once we throw away the map, we get a graph like this, and all we need to know now is how to color each of these vertices with different colors, so that no two adjacent edges have the same color, adjacent vertices. The reason is obvious, because two adjacent vertex or two neighboring vertex share a common boundary. So, we do not want to have them same color. So, we want to color them differently. And now, the question is that how many colors do you need to color the map of India? Is 4 sufficient? Is 5 sufficient? Is 3 sufficient? And so on and so forth. One can ask various questions on that form. So, if we have an algorithm to solve, then we end up coloring the map of India using those set of colors. So, this is a example of where graph can be used for coloring of maps. Similarly, there is another concept called independent set. An independent set is a set of vertices such that no two vertex in a set has any edge between them. For example, in this graph, say A and E is an independent set, because there is no edge between them. Similarly, D, C and G also is an independent set, because there is no edge between D and C, there is no edge between C and G, there is no edge between D and G. And the question is always to find out the maximum independent set. Why? Let us consider it. In a hostel, there are a set of people and each of them has their own preferences. So, Rahul wants to see a TV, the TV from 6 to 10. Joy wants to watch a completely different channel from 7 to 9, and John wants to watch another different channel from 8 to 11, and so on and so forth. Now, what is it? We want to somehow say that we want to satisfy as many people as we want, as we can. But of course, if we satisfy Rahul, we cannot satisfy Joy, because Rahul and Joy's timings are clashing. So, what do we do? First of all, we again draw different vertices for each of the people. Say this is Rahul and this is a Joy. Now, if Rahul and Joy has a clash, then we will add a edge between Rahul and Joy. Similarly, say this is John and John and Rahul doesn't have a clash, because Rahul can watch his program and then John can watch his program, but John and Joy has a clash. So, we again draw an edge between them. And similarly, if this is Anita, Anita doesn't have any clash with Joy or Rahul, but Anita has a clash with John. And say Pappu has no clash with anybody, so no problem. And Jack has a clash not with Rahul, but he has a clash with Joy, and he has a clash with John, but he has no clash with Anita. Now, after that, after this graph has been drawn, all we need to know is an independent set. What is the maximum number of independent set that we can get? And by looking at it, we can say that okay, like if we satisfy, one thing to do is that we can satisfy Anita, we can satisfy Rahul, and we can satisfy Pappu. So, maybe 3 people can be satisfied. Is it possible to satisfy 4 people in this graph? And that is why we need to understand how to solve a independent set problem in a graph. To highlight whatever I was saying, graphs are very universal and they are used to solving various day to day life problems, not only day to day life problems, many other problems in computer science and other subjects also. So, understanding graphs from purely its combinatorial value is very important, then we can solve many other problems. Now, once we have kind of understood that graphs are important, the next thing to understand is how is a graph given. So, how is a graph presented to an algorithm? As I told, a graph is not given in the way of which a drawing is done. And what is the size of the input? To understand that, there are 2 different usual standard ways of presenting a graph, representing a graph, and also that gives us 2 different sizes. For example, here is a graph, and what we do is that first of all we put this A, B, C, D, F, G, H, G in the on the row, and we slowly write down for each vertex whether we put a 1 if there is the edge between those 2 vertices and 0 otherwise. So, if there is the edge between A and B, we put a 1, if there is no edge between A and C, we put a 0, and so on, and we keep on doing it. And once we have done this kind of stuff, we get what is known as the adjacency matrix. The same technique can be done for a directed graph, and this also same technique can be done for a weighted directed graph, where instead of putting 1, we put the edge weight in that matrix. So, this gives us, if we consider the number of vertices as n and the number of edges as m, then the simple directed graph which has n square edges, and so the size of the adjacency matrix is n square. It is like, good thing of this is that one can access any edge in just one step. There is another way of doing it, which is called the adjacency list, where for every vertex we list out all its neighbors. This is slightly better, and here at size of the adjacency list is written as order of n plus m, where n is the number of vertices and m is the number of edges. So, advantage of the adjacency list is that it is short, and advantage of the adjacency matrix is that it is easy to access. So, this brings us to the end of this lecture. To summarize, we looked at graphs as combinatorial objects, we looked at applications of graphs, and then we looked at how a graph can be represented. In short, we have kind of convinced ourselves that graphs are very important objects to study. From next lecture, we will be looking at graph algorithms in more details. Thank you.